You will remember, this topic, I've been calling it integration, right? But really what it is areas under curves. That's where we started, do you remember? And it just so happened that Riemann and his clever idea of the Riemann sum and limits and calculus, blah, 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 worked out integration, this process was so close to differentiation, anti-differentiation, was a really great way of doing it. It's not just great, it's fast, it's precise, you know, and that's why, because it's so good, that's why we keep using it. Like, you know, if you've got a fast, precise method, it makes sense to build your topic around that method. Okay. So being that we have a fast, precise method for calculating areas under curves, why would we go backwards? Why would we come up with a method, or actually methods too, that are not only less accurate, but as you'll discover, most of the time, it's usually slower.
Because
why would we bother?
That is unintegratifiable.
Okay, now, two reasons. Number one, we've so far been working with, you know, functions where we know how to integrate. Okay, we know how to integrate. So, stuff like this, you know, we can eat for breakfast, yeah? But it's not that hard to think of functions which we can differentiate, but we can't integrate. And, you know, it's not complicated. Example, suppose I wanted an area under this curve. Now, you've known this about this function for months now. It's not hard to differentiate. How do you integrate it? And therefore find the area underneath. Okay? Now, at the moment, you guys can't. If you want to, later on, I'll teach you how to integrate this function. It requires a fancy method, or even fancier name, called integration by parts. But the point is, like, it's hard to work with, okay? But we can still work out its area. Now, firstly, what if my function is tough to integrate? Secondly, what if I don't even know what the function is? Like, what if you've got some measurements, okay, and what you want is the area underneath, okay? But what actually governs this function? You don't know what its rule is, okay? You don't know what the x to the power of this or whatever is. You've just got measurements. Now, think back. When did we learn how to deal with situations like that?
Yes,
you have questions like this. They're like, here's a lake, okay? And like, we have these measurements. Now work out what the area is, okay? So, yes. Okay, good question. We'll get to, I'm not going to cover it today. But the short answer is, number one, because you can. It's not that hard. Number two, because it's useful. Like, you get weird shapes, so you can work out the areas. That's a handy skill. Anyway, this is why we're going to learn methods for approximating areas. We're going to learn two. The first one is called the trapezoidal rule. And you might want to make that subheading. The second one is called Simpson's rule, but I anticipate we'll get to it tomorrow. Actually, I'm pretty sure we'll get to it tomorrow. Sorry. Okay, so how does trapezoidal rule work? Suppose I want to find an area like this.
So did we learn Simpson's rule in year 7?
Yeah. I think that's been said about
Welcome to the present, Robbie. Okay, now, if I want to find out what this area is, trapezoidal rule was very similar to the whole idea of the Riemann sum, which is chopping up an area into, you know, a shape which I don't know, into shapes that I do know. Okay, now what did Riemann use for his Riemann sum?
Infinitesimally of rectangles.
He just used rectangles, right? And when you turn it into a Riemann integral, then he just had a whole buttload of it. Okay? But it doesn't take that much to realize that you can do better than a rectangle by using a trapezium. Okay? So let's just take the simplest case of a single trapezium, right? If this is the area that I'm after, okay, so that's what I want. Okay? I can make a trapezium that'll be at least in the right ballpark as this by taking the tops of the two function values, okay, and just joining them. There's my trapezium. Okay? Now it's important to note that you know, these are vertical, so that's a right angle there, right? So how would I go about working, calculating, the area of this trapezium? What is the area of a trapezium? Like if I had, if I gave you one like this.
The average of the bases and top.
Okay, sorry, I heard it comes to half of what?
A plus B.
Yeah. Half of now. So it's half of this perpendicular height.
And A plus B.
And then you take the average of the two parallel sides. Okay, now you might notice I've deliberately not called them A and B, even though that's what we normally call them. Why? Because my A and B are my upper and lower bounds. Okay, so that's why I just watch out. So m plus n, you add them, and then taking on 2 gives you the average, and then you multiply by the height. So this is a standard way, right? Now, what do each of these things correspond to in our diagram? Well, where's the perpendicular height of this trapezium? It's that horizontal distance in there. Okay, now in this case, it's B minus A.
Oh, it's A. Which equals A.
That's a more surprising result than I thought it was. Okay, so this is B minus A, right? Now what are these two parallel sides equal to? Well, if that's x equals A, and that's x equals B, and this is f of x, okay, what's the height of the first one? And the second one is? Now these are important. Make a note of this. We need to introduce some terminology. The quicker I do it, the better, because it'll start to get confusing later. These guys, f of A and f of B, right? Because I get these heights, right, or bases, if you like, by evaluating the function, taking these values and putting them into the function. Okay, we call them function values. Okay. The questions will refer to certain numbers of function values, so it's important you know what they are. Okay. Right, now that I've got all my pieces, what's the area? So I can say, number one, the area is equal to the integral from A to B of f. Okay. But I'm now going to, so not equal to, I'm now going to say that's approximately equal to this trapezium that I've just manufactured. Okay. So it's this perpendicular height on 2, so B minus A on 2, okay? And then I'm going to take the average of the, I should already retake the average, I'm just going to add up the two functions. F of A, F of B. Okay? So you see, normally we would have said, at this point, what's this actually equal to? If you know what the primitive is, then you evaluate it at your upper and lower bounds. But the point is, I don't know what the primitive is, or I can't be bothered to calculate it. So you can see if we're going from here to here, number one is approximate, number two, I just need to know what the original function is. No sweat. Okay. Now, as you can probably imagine, this trapezium that we've just manufactured might be a good approximation, or it might be a lousy approximation, right? So if I give you a function like, say, I don't know, let's think of one. I draw one down here. Something like this, okay? And suppose I want to find its area from, say, there's my A, up to here, to B, right? Well, the trapezium you make out of this is like 5 times the size of the area that I'm actually after, okay?
Indeed.
So trapezoidal rule, highly dependent on, what kind of function you are as to how close you get, right? But I can still use trapeziums in a situation like this to get a pretty good approximation. What would I do instead? I would just do the same thing Riemann did, which is have more of them, okay? So if I put in a trapezium here, and a trapezium here, and so on, the more trapeziums I get, the more shapes I get, the closer I'll get. The less this error area will be, okay? So how do I generalize it? Draw yourself another graph, just like this one. And now I'm going to go from, this is kind of like basic trapezoidal rule, 1 trapezium, 2 function values. What happens if we have more? So